Welcome to this University Utara Malaysia session on the roots of artificial intelligence, developed by Dr. Ala Jabar Al-Maliki. When most students start studying AI, they picture screens full of Python code, algorithms, and servers. But writing code is only a fraction of the process. To actually simulate intelligent behavior, we have to pull concepts from far outside traditional computing, drawing on 8 distinct scientific and engineering domains. This chart maps the foundation of artificial intelligence. It branches into philosophy, mathematics, economics, neuroscience, psychology, computer science, control theory, and linguistics. By the end of this module, you will explain the structure, identify each root's contribution, and understand how they build intelligent systems. Without this structural map, a developer is limited to writing code, without understanding the underlying logic, ethics, or feedback loops that allow an AI to function in the real world. Let's break down those roots, starting with philosophy. Before a machine can make a decision, we have to define what knowledge and rational thinking actually are. Modern AI ethics, specifically how we filter out bias and ensure fairness, relies entirely on philosophical principles. Taking those philosophical rules and making them computable requires mathematics. We use linear algebra to structure neural networks and calculus to drive the optimization algorithms, like gradient descent, that minimize our prediction errors. When an AI needs to make a decision with limited resources, it uses economics. Concepts like utility, gain theory, and cost-benefit analysis allow automated trading systems to evaluate financial risk and map out the exact strategy for maximizing returns. Moving to the biological side, neuroscience provides the physical blueprints for AI architecture. By studying the human brain structure, researchers designed artificial neural networks. For example, convolutional neural networks imitate our biological visual processing to recognize objects in images. Psychology studies cognition and behavior. Understanding how humans learn and perceive information allows us to build behavioral models. When a recommendation system analyzes your past choices to suggest a movie, it is applying psychological theory. We have established ethical rules, mathematical engines, biological architectures, and behavioral models without writing a single line of execution code. To actually execute these theoretical models, we need computer science. This discipline provides the required hardware, databases, and programming languages. It gives us the AI frameworks like TensorFlow and PyTorch in Python to make the algorithms run. When an AI operates in the physical world, it relies on control theory and cybernetics. These fields govern feedback mechanisms. If a drone or a self-driving car encounters a sudden obstacle, control theory allows the system to adjust its motor output based on those environmental changes. Finally, for an AI to communicate, it needs linguistics. The study of grammar, syntax, and semantics forms the foundation of natural language processing, which is exactly how tools like ChatGPT parse the meaning of your prompts and generate coherent text. Let's test how this comes together. Look at this self-driving car. If you had to identify which specific disciplines handle optimizing the fuel route and which handle the continuous steering and speed adjustments, what would you say? Route optimization for time and fuel efficiency comes from economics. Steering and speed control come from control theory, and the rest of the car uses the others. Neuroscience designs the computer vision networks, psychology models the behavior of surrounding drivers, and philosophy dictates the ethical decisions in a critical crash scenario. Pulling any single discipline out of this blueprint compromises the entire autonomous system. Applied AI relies strictly on this deep interdependence to function. This table maps all 8 roots to their specific contributions, showing exactly where logic, optimization algorithms, and feedback systems originate. This multi-field integration has distinct advantages. It builds highly capable systems for complex problems and accelerates innovation by forcing experts to collaborate. But that integration is difficult. Combining diverse knowledge requires immense cross-domain expertise. As these systems become more capable, the ethical, legal, and social friction increases heavily, demanding careful coordination among specialists. Engineering these integrated systems requires stepping outside the silo of computer science. By mastering these 8 multidisciplinary roots, you gain the framework needed to build machines that can perceive, reason, and act within human environments.